Now that we've fully defined the problem, we need to consider the different ways of solving the problem and choose the most appropriate solution. Now we need to determine what type of problem we're solving. So we know that there's a cryoprobe that's holding this surface at minus 196 degrees Celsius. And we know that this surface is 37 degrees Celsius. So there's clearly some temperature gradient here that is causing heat to be lost in this direction. We also know that there's no bulk flow through our material or through our layers. So we can conclude that this problem is simply a conduction problem or some derivative of a conduction problem. We're also told to assume a steady state. So we can use our steady state analysis to solve the rest of this problem. We will be using our steady state flowchart to help us formulate the rest of this solution. Looking at our steady state flowchart, we can determine how many ways there are to solve this problem. First, we need to determine whether or not heat is being generated. Because the problem makes no mention of heat generation, we can assume that there is none. This leaves us with two different possible solutions. We can either start from scratch or use a resistance analysis. So now we must determine which approach to use. We have two options. We can use a resistance analysis or a from scratch approach. The question is, which one should we choose? A from scratch approach for this problem doesn't really make much sense because we have three different layers, each with different thermal conductivities. Hence, modeling this system using just one general equation is going to be pretty difficult. Instead, a resistance analysis makes more sense because we have two temperatures specified over a given length, so we can find our heat flow using our equation delta T over R, which will also allow us to find the heat flux and help us solve the rest of this problem. Pretty much any time that we have multiple layers in our system, we're most likely going to be using a resistance analysis. If we continue along our flow chart, we need to answer some questions. We need to know how many resistances we have and whether or not they're in series, parallel, or they're in some mixed configuration. Looking at our schematic, it's clear we have three layers in series. Because these three layers are in series, we know that the heat flux through any two surfaces in our system is the same. So if we call this layer 1, this layer 2, and this one layer 3, the heat flux through surface 1 or layer any surface in layer 1 is equal to the heat flux through any surface in layer 2, which is equal to the heat flux through any surface in layer 3, which we could say is just equal to some heat flux Q. Because we're not dealing with any cylinders or spheres in this problem, it seems pretty obvious that we will be using a slab geometry. And because we're using a slab geometry, we know that the resistance equals the length over the thermal conductivity times the cross-sectional area. So as we derived before, we know that the heat flux through each layer is the same. So we need some way to find the heat flux given our resistance equation. We can do this by starting with the heat flow equation, which we know is Q equals the change in temperature over the resistance. We also know the relationship between heat flow and heat flux. The heat flow is simply equal to the heat flux times the cross-sectional area. So we know that the heat flux equals the heat flow, Q, over the cross-sectional area. So we can relate these two equations to come up with an equation for heat flux in terms of resistance. And by doing this, we get the heat flux is equal to the change in temperature over the resistance times the cross-sectional area. And we can plug in our equation for resistance to get the change in temperature over L divided by K times A times A. And if we simplify this, we get something that looks a lot like the Fourier equation for heat flux. Now that we have our equation for heat flux, we can find the heat flux through each of the layers and then solve the rest of the problem.